Astronomers have witnessed a black hole twisting the very fabric of space-time by its rotation. A report in the journal Nature claims the black hole's powerful gravitational pull is literally dragging nearby space-time, causing jets of fast-moving energy and plasma being expelled from the area around the black hole to wobble so fast that their change in direction can be seen in periods as short as minutes. The authors were studying V404 Cygni, a stellar mass black hole about 9 times more massive than the Sun, located about 8,000 light-years away. V404 Cygni first came to astronomers' attention back in 1938, when it experienced an outburst and got its initial designation as a variable star. Another outburst was observed in 1989, and follow-up studies revealed a previously unnoticed outburst in 1956. NASA's Swift Space Telescope detected the latest outburst on June 15, 2015, triggering a worldwide observing effort. The authors made their observations using the National Science Foundation's Very Long Baseline Array of radio telescopes. The array began its observations on June 17, 2015, and continued for almost a month through to July 11. They found the black hole was drawing in material from a companion star, with a mass about 70% that of our Sun. Now, as material streams towards a black hole, it forms a rotating disk called an accretion disk surrounding the black hole. And this accretion disk becomes denser and hotter with decreasing distance from the black hole's event horizon, the point of no return, beyond which material will disappear in the black hole, falling forever towards the singularity. But some of this superheated material on the accretion disk can escape before reaching the event horizon, travelling along magnetic field lines to be shot out as microquasars. And the material being ejected from V404 Cygni is travelling at some 60% the speed of light. However, the astronomers noted that the black hole's rotational axis is precessing, possibly because of the gravitational pull of the companion star upon which it's feeding. And so the jets aren't stable, but instead rapidly wobble. The study's lead author, Associate Professor James Miller-Jones from the Curtin University node of the International Centre for Radio Astronomy Research, says he's never seen an effect like this happening on such short timescales. Such a rapid wobble has simply never been seen in such systems before. The phenomenon can best be explained when viewed through Albert Einstein's general theory of relativity, which shows how massive objects, like black holes, distort the very fabric of space-time, giving the effect we all know of as gravity. And as such massive gravity wells as black holes spin, their incredible gravitational influence pulls space-time around with them through an effect known as frame dragging. In the case of V404 Cygni, where the black hole's spin axis is misaligned from the plane of its orbit with the companion star, that causes the frame dragging effect to warp the inner part of the disk. Then pull the warped portion around with it, which changes the orientation of the jets, producing the wobbling effect observed by Miller-Jones and colleagues. Miller-Jones says it's the only mechanism he can think of that explains the rapid precession seen in V404 Cygni. He says you can think of it as the wobble of a spinning top as it slows down, only in this case the wobble's caused by general relativity. While V404 Cygni's accretion disk is about 10 million kilometres wide, Miller-Jones points out that only the inner few thousand kilometres or so is warped. And that inner part is also puffed out by strong radiation pressure into a donut shape that precesses like a rigid body. Interestingly, the jet's rapid direction changes also meant that the authors had to change their observation strategy. See, normally astronomers would produce a single image using data collected over several hours, very similar to a long-term exposure. However, these jets were changing so fast that in a 4-hour image, all they really got was a blur. So to capture the rapid motion, the authors made 103 individual images, each about 70 seconds long, and then combined them to make a movie. Miller-Jones says similar behaviour would be occurring in other black hole systems. It just hasn't been documented at this rate before. He says the discovery will therefore deepen science's understanding of the physics of black holes and the environment surrounding them.
This is a very exciting black hole system that we've been looking at. It went into a very bright outburst. So the black hole started feeding very rapidly in June of 2015. And we looked at it with the National Radio Astronomy Observatory's Very Long Baseline Array. So this is a very high-resolution radio telescope. It's made up of 10 dishes spread across the US from Hawaii to the Virgin Islands. And that allowed us to zoom in to see the details of the jets that were being launched by the black hole and how they were evolving. So when we looked with this telescope at this rapidly feeding black hole, we saw something fairly unexpected. So we saw that instead of moving in a single direction, the jets appeared to be moving in different directions at different times. And that's never been seen before, at least not on this very short time scale. So within a single 4-hour observation, we saw that the jets were moving out in different directions. And we had to try and figure out why that was occurring. The black hole in V404 Cygni is only about 9 times the mass of the sun. So it's not a particularly big black hole in the grand scheme of things. The supermassive black holes that you find at the centers of galaxies are millions of times bigger.
We shouldn't consider these quasars then?
No. They're something that we call microquasars. So black holes are very simple objects. They have a mass, a charge, which is usually 0, and a spin. And so the physics around black holes should be very similar, whether you're looking at one of these fairly small black holes, just a few times the mass of the sun, or one of these supermassive black holes in quasars. So we see the same kind of physics around both types of black holes, but because these ones are scaled down, they're sometimes called microquasars.
Okay.
So the jets in this one, we saw on a size scale probably about the size of our own solar system, and that was the kind of scale to which we could zoom in with our radio telescope.
Was this a rhythmic thing, this wobble you were seeing, or was it more staccato than that?
We think it was probably more staccato. So we could only see the jets moving out when they emitted the brightest bursts of energy. So these jets are carrying a huge amount of energy away from the black hole at speeds we measured of about 60% of the speed of light. So they're really powerful, very energetic things, but we only saw the very brightest ejections of energy. And so we saw about 12 of these over a 4-hour period. And so we couldn't, with only those 12 ejections, we couldn't say exactly whether they were swinging around regularly or not. But our explanation for what's going on suggests that this is much more likely to have been a bit of a staccato type scenario where it's not a rhythmic wobble as we've seen in some other systems on much, much longer timescales.
Like neutron stars, yeah.
Yes, and also a system called SS433, which is a very well-studied system where we see swinging jets that describe a corkscrew pattern on the sky. Mm-hmm. In that system, the jets are swinging around on a timescale of about 6 months. In this case, we think it was a timescale, well, it was certainly less hours, if not minutes. So that's thousands of times faster. And so we needed a different physical mechanism to actually cause this.
What do you guys think's doing it?
So what we think is going on is that we think that the black hole is spinning, and we think that it's spinning around an axis that is different from the axis of the orbit of the companion star. So this black hole is feeding on a companion star. It's in a 6.5-day orbit with a star that's about 70% of the mass of our sun, and the outer layers of the star are being pulled off and falling in towards the black hole. So we think that orbit is around a different axis to the spin of the black hole. So that means that when the material gets close to the black hole actually, because of its strong gravity, Einstein's theory of relativity tells us that it pulls space-time around with it. And so this means that the gas is forced to move around in the direction of the spin of the black hole. But there's a region, therefore, where the gas has to go from rotating in one plane as it swirls around the black hole in a disk to rotating along with the black hole itself. Because the black hole was feeding very rapidly, the intense radiation that it was generating puffed up the inner few thousand kilometers of the accretion disk, the disk of gas that's swirling around the black hole. So this whole disk is about 10 million kilometers across. Just the inner few thousand kilometers was puffed up into a sort of a donut shape, if you like. And we think that because of the misalignment between the orbit and the black hole spin, that donut was being forced to precess, so basically wobbling around an axis, much like a spinning top would as it slows down. And we think that precessing inner part of the disk was actually pulling the jets around with it, and that was what was causing the redirection. So it's a very exciting demonstration that what's going on these very, very small scales right down in the black hole is affecting the jets on much larger scales out to the size of the solar system.
That's Associate Professor James Miller-Jones from the Curtin University node of the International Centre for Radio Astronomy Research.